Event Data Project, otherwise known as ACLED. I'm pleased to be moderating today's session on machine learning and natural language processing techniques and how they can be applied to conflict data specifically. We hear the terms machine learning or natural language processing or NLP often, especially as our field is starting to leverage data and quantitative analyses to better understand conflicts around the world. These techniques rely on large sets of data, whether it's event data of conflict incidents or large blocks of text that you might gather from peace agreements, treaties, or other reports. These data are then fed into various models that use it to make predictions, categorizations, or other analyses. Researchers can use these techniques for lots of different outcomes. It can be limited to analyzing very specific historical contexts and conflicts. It can be expanded to predicting future conflicts to some degree. At ACLED, for example, we've created the Early Warning Hub, which combines traditional statistical analyses and predictive modeling to produce a series of tools that can give early warning to practitioners about potential emerging conflicts around the world. For our internal processes, we've also begun to leverage natural language processing and text classification to assist our researchers in categorizing the causes of protest events. Rachel Goodman is with us today on our panel from ACLED to discuss this work further. Other organizations are also using these techniques to identify new events that might fall into various event types. At the Carter Center, Kate Keeter and her team worked on reclassifying conflict data from ACLED into new categories that were useful for their internal processes. She'll discuss how they approached this, the challenges they faced, the lessons they learned from undertaking a complicated project like this. Similarly, at Extract, Matt King and his team used artificial intelligence and machine learning to identify weapons being used in certain events, classify Daesh propaganda into themes, and to find similar content that might also be relevant for their work. He'll discuss the types of AI and machine learning that they use to do this, the challenges you face in this type of work, and how to set up your data to successfully run these types of models. Another of the popular uses of machine learning or NLP work is with harnessing social media. How can tweets or Facebook posts be captured, distilled, analyzed to tell us information about public sentiments, trends, or even predict protests or conflicts? Anuswa Trivedi from Microsoft's AI for Good Research Lab will walk us through how she and her team built a web-based tool for detecting and analyzing disinformation on social media for Carter Center's democracy program. And for those of you who are curious about how to start leveraging these models in your own organization, whether or not you have a data science team, the good news is that places like Extract or Microsoft's AI for Good Research Lab are working to make these techniques more accessible, especially to smaller organizations. So that being said, you can see that machine learning and natural language processing can not only lend a lot of insight into our field, but it can also be a useful tool for making our research more efficient. Even with its many uses, one thing that you'll find all our panelists probably agree on is that no matter the work you're doing, it's important to identify what type of model is most appropriate for your project, structure your data accordingly, and make sure you take the results with a grain of salt. Machine learning can be a wonderful tool for peace building, but it's not a replacement for the expertise and the insight of researchers. Our panelists will highlight how they're using these techniques in their organization's work through a series of presentations today, and then we'll open it up to questions from myself and from the audience. So we'll begin with Rachel Goodman. Rachel is the data coordinator at ACLED, where she executes the planning, coordination, and implementation of new technologies and approaches to improve and streamline ACLED data. Rachel, take it away.
Hi, thanks for that intro, and thanks to everyone for being here. Let me share my screen. All right. So as Kadian said, my name is Rachel Goodman. I'm the data coordinator at ACLED, and today I'm going to be talking specifically about natural language processing and its use in identifying protest drivers within ACLED data. So for those of you who aren't familiar with ACLED's work, we are an independent NGO that was born out of an academic project several years ago. And we have a global team of researchers who collect and maintain a data set of political violence and demonstration events. Currently, this data set covers over 200 countries and territories worldwide. And our temporal coverage depends upon the region, but our longest running set of data spans from 1997 to the present. And all of our data are publicly available on our website, and they're updated every week. Now, in our data set, the fundamental unit of analysis is the event. So we take reports of political violence and demonstrations, and we break them down into individual discrete events. We, we disaggregate them by date, by actors involved, and by location. We also assign event types to all of our events. We don't have a ton of time to get into that today, but just for the purposes of this presentation, we will just be looking at ACLED's protest event type. So all of the data that I talk about today will specifically be protest data. And it's also important to note for today's discussion that all of our events include a short description in our notes column. And this usually is just 1 to 2 sentences about, that gives you additional information about the event, additional context. So if you were to look at one of our protest events, in the notes column, you would find information about the particular cause of the event or the driver, the protest motivation. And although we have this information in the notes, it's not necessarily standardized. So different researchers may be using different words or different phrases to refer to the same protest motivation, which means that it's difficult to harness this information for broad analysis. So we've been looking into introducing standardized protest driver tags to facilitate analysis of protest trends using ACLED's data. Now, the problem with this, or the challenge that we're facing, is that in order to add these tags, we would need to retroactively add them to all of our historical data, which would be extremely time consuming. So the question then becomes, how do we reduce the amount of time and the amount of work that's required to add these new protest tags to our existing data? And one potential solution to this is natural language processing and text classification. But in order to test out this approach, what we first need is a set of protest events that already have protest driver tags added. Luckily, we actually have that. So our US data, which runs from Jan 1st, 2020 up until the present, already has protest motivation tags that were manually added. And the protest tags include things like pro-Trump, pro-Biden, anti-abortion. This list isn't comprehensive. This is just to give you an idea of some of the tags that we do have in the US data. It's also important to note that these tags are not mutually exclusive. So an event can have multiple tags, it can have just one tag, or if it doesn't fit into any of these categories, it can have no tag at all. So since we have the US protest data with protest driver tags already incorporated, we were able to use this data to train a text classification model that would assign protest driver tags for us. So the first step was splitting the US data into a training data set and a testing data set. So we put about 3,000 events into the training data set, which, as the name suggests, is what we use to train and build the model. We put about 30,000 events into our testing data set, which, again, as the name suggests, is what we use to to test the model and to test its accuracy. And the reason that we used such a small training data set in this case is because we wanted to test the feasibility of training future text classification models with a similarly sized set of data. If we were to implement something like this in the future, we want to make sure that our researchers don't have to manually tag tens of thousands of events in order for this sort of modeling to be effective. So that's why we have such a small training data set in this case. So the next step was training and running the model. We opted to use what's called a support vector machine with a linear kernel. And don't worry if you don't know what that means. This is definitely some technical jargon, but what you really need to know about this is that it's a machine learning model that's really popular and really useful for text classification. So this is the model that we opted for. And we actually trained 11 separate models, one for each of 10 protest tags and one for a no tag category. You can see all the tags listed here. And our models looked at the notes column that I referenced earlier. It looked at the words that were in the column, and then based on that, it calculated the probability that a given tag should be assigned to a given event. And if that probability was above 20%, we went ahead and assigned the tag to the event. And you might be wondering why we set the threshold so low, and that's really what I'll be getting at over the next couple of slides. We'll be discussing the reasoning behind why we set the threshold at 20% and the benefits and the downfalls of that. Now, this slide is showing you a sort of visual representation of the model's results just for one particular event. So this, you can see the notes, I've included them here. This was a protest event in Lincoln, Nebraska, where protesters were demonstrating against the city's mask mandate. And many people at the protest were also displaying pro-Trump flags. So the correct tags in this case, the tags that were added by our human coders, our human researchers, they added the anti-COVID restrictions tag and the pro-Trump tag. Now, if you look at the graph here that's showing the results from the model, we actually have 3 tags that were assigned by the model, 3 tags that exceeded that 20% probability threshold. And we can see that the anti-vaccine tag in this case is actually incorrect. So the model assigned it, but it should not have. And if we were to implement a text classification model in the future to add protest driver tags to other countries or other regions, we would need a human reviewer to review these tags to make sure that they were actually correct. So in this case, a reviewer would look at this event, they would look at the notes, and they could see that the assigned tags were not all correct. And they would recognize the anti-vaccine tag was wrong in this case, and they could simply remove it. On the flip side, if we consider sort of an alternative option here, if we had set the probability threshold at 70%, the model only would have assigned the anti-COVID restrictions tag, which means a reviewer then would need to recognize that the event was missing the pro-Trump tag, and they would need to add it in. And this starts to get at why we set the threshold so low, because oftentimes it's easier and quicker for someone to remove a tag that's incorrect, as opposed to having to recognize that there's a missing tag and then add that to the event. So as we decrease that inclusion threshold down to 20%, we're decreasing the number of tags that are missing from the events. But on the flip side, we are increasing the number of tags that are incorrectly added to the event, or the number of events that we call overclassified. So when we add an incorrect tag to the event. And on the aggregate, this is kind of what that looks like. So this shows you the percent of human tagged events that were correctly tagged by the model. You can see for anti-COVID restrictions, out of all the events that should have been tagged anti-COVID restriction, the model actually did tag 99.5% of them. So we only missed less than 0.5% of the events in this case. So what this is really showing you is that we really, with that 20% threshold, we really missed very few tags. But then on the flip side, as I said before, this means that we are overclassifying more events. This graph is showing the percent of machine tagged events that were correctly tagged. So for, let's say, pro-immigration, out of all the events that received the pro-immigration tag based on the model, only 39% of those actually needed that tag. The other 61% were incorrectly tagged. And the numbers on the right give you the absolute number of events that were incorrectly tagged for each category. So the number of events that were overclassified. So with that being said, I think one of the major takeaways from this is that we definitely need to do some further testing to optimize that inclusion threshold, because what we're really dealing with is an issue of a trade-off between missing tags and overclassifying events. And so for each tag, we need to find sort of that middle ground where we're minimizing the number of missing tags, but also where we don't have so many overclassified events that our reviewers need to correct. So this process was really sort of a first step for us. So our next steps are just going to be working on testing different inclusion thresholds for each tag to see what works best. But even with these caveats and with these challenges, I think we can see that NLP is certainly has a lot of potential to be an efficient alternative to manually adding these tags to our historical data. And more generally, I think, as we'll hear, I'm sure, from the other panelists, NLP has, and text classification more generally, they have a lot of potential for broader application, not just across ACLED data, but across Peacebuilding data in general. So with that, I will end my presentation there, and I'm happy to answer any questions you have at the end. Thank you.
Thanks so much, Rachel. That was great. Next, we have Kate Keeter from the Carter Center. Kate is a peace builder with a background in mediation and Middle East politics. She worked on the Carter Center's Syria conflict mapping project for many years and recently joined the organization We Power to support community-focused positive peace initiatives in St. Louis. So Kate, please go ahead.
Thank you. Let me go ahead and share my screen. Can everyone see my screen and not my presenter's notes? Together, yes. Perfect. All right, just want to make sure. All right. Hi, everyone. My name is Kate Cater, and I am representing the Carter Center's Data and Analysis team. I will be sharing my experience with the natural language processing tool that my team built with Microsoft's AI for Good team that Anusia is here representing. This is a project specific focus from a non-technical individual. So just FYI, I won't be able to give you the ins and outs of our model exactly, but I want to share my top 3 lessons learned. And those are that data hygiene is important, especially when using a text classifier with conflict data. That automation can catch human errors, especially if you're doing that necessary human validation during the testing. And then lastly, that you need to invest in the people and processes to train and maintain an automated solution. But first, why, right? Why use machine learning? I think that's always a really good question to ask at the start. So this team has been tracking conflict dynamics in Syria since about 2013, and it's to support the Carter Center's own conflict resolution efforts in Syria, as well as the efforts of other international mediators. And we've been conducting our own data collection for about 5 years, but needed to pivot to an external data source. And that's when ACLED came in, and it was great. But they classify their incident types differently than we do. So in order to be able to analyze our data over time, we needed to have our structure of the data line up. And we were doing that by spending about 4.5 hours per week reclassifying and transforming that information, which, being short on staff and short on time, which I think many people can empathize with, it wasn't sustainable. So we felt that we needed an automated solution. So we turned to Microsoft's AI for Good team, and we were connected to them through the AI for Humanitarian Action grant that we applied for and got. And Anusia and her team, after speaking with them, identified that a deep learning text classifier would be our best approach to addressing our problem. And they decided to use BERT, which is a natural language processing tool, as the base model. And BERT stands for Bidirectional Encoder Representations from Transformers. Do I know what all that means? No, not really. But I learned a lot from Anusia, and I got to know the outputs of this model fairly well. So, like I said, we learned a lot. First, data hygiene is important, especially when using a text classifier on conflict data. And like Rachel pointed out, with an ACLED, you have the notes section, right? So with our data, oftentimes you have conflict events that are being translated from Arabic to English, or a non-native English speaker reporting conflict. So that means that the grammar is messy and the descriptions can be inconsistent. So you want to make sure that you are categorizing your incident types in a consistent manner and keeping track of what particular words mean, because our lexicon changes over time. And that's the same for describing conflict. So we saw, for example, that if we applied the NLP to our earlier data, 2013 to 2014, let's say, it just didn't make sense, because the way that the conflict was described and incident types were described was different than how it was being described in 2018 and 2019. So we really focused on more recent data, the data that we were pulling from ACLED. We also retrained our model in January of 2021. So for example, this graphic shows the change in confidence intervals over time from August of 2020, when we first started using the NLP, to November of 2021. And I want to point out that this axis is very small. It's a range of a 84.6% confidence interval and an 85.6 confidence interval. So very tiny changes, but it's interesting that you see this constant gradual improvement. And there's that little kind of jump up when we retrained it in January of 2021. But if you take a look at now our IED confidence interval, or improvised explosive devices, you can see that it's been decreasing over time, and it kind of jumps down a bit in January when we retrained it and continues to decrease. Again, very tiny decreases. It's a confidence interval of 89.9% and 89.6%, so tiny, but we kind of digged into that a little bit, and we're suspecting that just the way that IED attacks have been described over time has been changing. So that language that we've been training the NLP on how to identify an IED attack is not staying the same. And we need to account for that. And it underlies the importance for us that you need to be clear on what words mean and how those standards will affect your training. And it also raises questions like, should we decide a cutoff point of using our current version of our NLP on a certain time frame of data and then updating to a new lexicon of data and applying it to more recent data? It's really important if you're using text and language as your way for training your model. We also learned a lot with human errors. Automation can catch human errors, especially if you invest the time in human validation during that training process, which is just good practice, but we really learned just how great that and helpful that can be. So we are finding that some of our analysts were occasionally misclassifying incident types, which it happens, we're human. You're looking at hundreds of data points a day sometimes. So that model caught that human error. So if we put the true label as clashes, but it's really aerial bombardment and shelling, our model still accurately put the correct aerial bombardment and shelling because we were really thorough in marking what was the correct incident type and what language goes for it when we were training and validating the data. And we also saw that it maintained a pretty high confidence level when analyzing multiple incident types in a single conflict. So it has a 84% confidence level when an incident has two incident types, let's say shelling clashes, compared to an 87% confidence level when it's just one type. That's pretty cool. It's telling us that this multi-label classification is not bringing down the confidence level of our model. We also saw that's pretty confident in its outputs. We just have a confident model overall. So we have a range for ourselves that if it's returning a 50 to 64% confidence interval, we need to review it. We tag it as human review. And you can't really see it on the left-hand side, but it's kind of the percentage of need human review for each of our incident types. And overall, we saw that less than 1% of our data falls into that needs human review category, which is great, except for clashes. The way that clashes are described within the data set keeps changing and shifting based on the reporting and how it's logged. So that's about 4% of the data that's being logged as needs human review. But that's still really great. And we like to see that nice big spread of in this other graphic, that spread of confidence. So it's either really confident that it's not this incident type or really confident that it is and not unsure in the middle. So lack of uncertainty is really great to see. You can see here for clashes, excuse me, that it's a little uncertain. Lastly, we learned that you need to invest in the people and processes needed to train and maintain an automated solution, which sounds obvious, but it's something that we continue to learn. It was great that Microsoft made it a goal to hand over the maintenance model to us and make sure that we have ownership, but that meant that we had to make sure that we maintain the time and investment to train and learn this data. So it took us several months to prep data and train it and improve it before we went even to production. So while now it's doing a lot for us, it took me time to realize that I wasn't going to just immediately remove the 4.5 hours a week I spent reclassifying data. I'd be replacing it with building this model. And that's something that I think as a nonprofit, it took us time to realize. So just a quick review, the lessons learned were that, data hygiene is important, especially if using text to classify conflict data. Automation can catch human errors, which is great. And you need to invest in the people and processes to make this happen. Really appreciate your time and feel free to reach out to my colleague Hampton, who's leading this project. Thank you.
Thanks so much, Kate. That was great. Just a quick reminder to everyone watching, you can at any point in time put comments or questions in the chat box. And we'll sort of be collecting those during the course of the panel and then having a Q&A session towards the end. So feel free to put any questions or comments there as we go along. So next we're going to turn to Matt King. Matt is the co-founder of Extract, which combines real-time attack and communications data with artificial intelligence to provide actionable insights for counterterrorism and countering violent extremism policymakers and practitioners. So Matt, please go ahead.
Great, thank you. I managed to share the screen before I unmuted myself there, so hopefully now you have it on the screen. I'm Matt from Extract, and I think our main objective can be described as to reduce the impact of extremism and hate speech, and particularly today, I just wanted to go through some of the challenges, some of the reasons that we're using machine learning and how that applies particularly to the text data. And I think that is an important kind of distinction to draw, that today we're mainly talking about text, but of course, when we're talking about conflict data, there's a huge amount of imagery as well. And a lot of what we do is not just the text, but working with image data and how we combine the two to find value in it. Like some of the speakers before me have said, I sit really, I suppose, in between technical and maybe the pure operational. And so I think this is maybe one of the lessons that we have learned, that there's almost new roles emerging that are neither purely what we would see in development, humanitarian and security as purely operational, but neither are they purely technical. And it's really learning the language to be able to translate between the two and translate particularly that operational requirement into a technical requirement for the machine learning engineers. So particularly for us, I think there are the 3 V's that are sometimes talked about in terms of data in the current era and the challenges that they pose. And that is the pure volume of data that we receive, just how much data there is out there, whether it is through social media, kind of open social media like Twitter or Facebook, or through Telegram, through websites, through huge amounts of sensor data. There is just an unprecedented amount of data about conflicts out there, and it's not in one format. It's not about one thing. It varies hugely in terms of the content and also the type of data. And to compound all of that, it's moving at an incredible pace. I think some of the speakers have already mentioned about how language moves on, how language changes over time, and how that potentially affects the reliability of AI or machine learning models in terms of their predictions. It's also spreading. It's spreading at a huge pace, and keeping up with that creates a number of challenges for anyone involved in working in conflicts. And so when we think about that volume, variety, and velocity of data that we are ingesting, it occurred to me that there are a number of problems that we face, and these are just 3 of them that I saw as being overlapping for us and relate to some of the examples that I'll give you. So the first is, how do we create order from that data? How do we actually create a system in which we can then generate the insight from that data? And as part of that, how do we find the data that we need at the time that we need it? How do we reach into that data set and actually pluck out the important piece of information? So this is where for us, AI and ML comes in. And I kind of use the two terms interchangeably in this. I don't think there is a lot of time to go into all of the details, but there's a spectrum, I think, that people talk about in artificial intelligence that goes from the very simple to the very complex. And our experience has been that it's not always the very complex that offers the best solution for the problem. We try to look for the simplest solution to the problem. And by simplest, I don't mean easiest, I mean the one that most effectively solves that problem with the fewest resources. So not everything needs a deep learning model, for example. And there are three particular types of machine learning and AI that I'm going to just briefly talk about here. Rule-based, semi-supervised transformers, and unsupervised. And so the rule-based models are the simplest, really, of what we're doing. And as I've put here, and as the name suggests, they're based on rules. And so it's very much, if you imagine sort of if-then functions, it is a set of rules defined by a human that the artificial intelligence then applies to a data set in order to find something. Maybe it is identifying weapons within, like here you can see a dash statement where they have announced the results as they see it of an attack. It might be identifying a target within it, such as a Nigerian army barracks. We may then want to classify that as Nigerian military, and we may have a number of if-then rules that would cover things like Nigerian army barracks, vehicle, soldier, all within that classification of Nigerian military as our own category of target. So that's one way that we use AI. Another is transformer classification, which is, I suppose, a little bit more technically complex, but brings with it complexities in terms of actually how we build it. And as was referenced in some of the previous presentations, how we cope with labeling data. And I think that is something that for us has been a big challenge that I'll talk about in a second. Here, just to make it specific, what we did was build a transformer model that classified Daesh propaganda into different themes so that we were then able to apply it in real time to their propaganda in order to understand more effectively at any given point in time, in any given place in the world, how ISIS is presenting themselves, how are they presenting their actions through their communications, and therefore those that are pushing back against violent extremism and the propaganda of violent extremists, how can they more effectively understand this content and try to do something about it? And as I mentioned, labeling the data, or rather, I should say, it requires a large amount of data for some of those models. And actually labeling that data so that if it's a tweet about disinformation, the model can recognize it as disinformation. If it is a theme such as military or religion, etc., for ISIS, your model can identify it as such. Generally requires a large amount of data for some of these deep learning models. And so the approach that we have taken is one called weak supervision, which really replaces some of those challenges that were being spoken about of hand labeling. So whereas going through it and literally labeling each sentence or each piece of text as Daesh propaganda, as military, as a particular event type, as whatever it might be, is incredibly laborious. It is slow, it can be expensive, it can mean exposing your data to third parties if you use an outsourced labeling force. And it also makes it really difficult to iterate it. So again, as was spoken about, I think in relation to things like IED, where we saw the change in accuracy of the model as the conversation and as the way that that attack type of IED was being described. When we're hand labeling data, it really means that we have to go back and relabel a whole data set again. This idea of weak supervision is really about injecting domain expertise into labeling. So a domain expert will come up with a number of heuristics, these kind of shortcuts or rules of how what an IED attack looks like in terms of language. And then we use those to automatically label the data. We then model those labels to understand where they conflict with each other, how much of the data they actually cover. And we then weight them with the final data set in order to create a complete data set that you can train your deep learning or other model on. And the advantage there is that when the conversation changes, when you get data drift, you can go back, simply change the rules, press relabel, and it happens very quickly. And this has really changed our ability to label data from what could have been, or what was months and months of labeling before, to hours. And I just put at the bottom a link. That's the system that we actually use for applying this system of weak supervision and labeling to our data. And then finally, we use an approach called unsupervised, which doesn't require any labeled data and is often used for clustering or grouping similar pieces of data. And so this is maybe where, or one example of where we use it is for finding similar text or images within our data set. So not just where the same words are being used, but where the meaning of the sentence, the meaning of that post, is actually similar to another. And this is a way of finding those similar posts that are maybe talking about an IED attack in one set of language, but then someone else saying an explosion, another saying a bomb was detonated. It's about finding the similar meaning rather than the similar words. So that was a very quick run through of just some of the AI and machine learning that we're using and how we're using it, hopefully to give you an idea of how it could be applied in your own projects.
Perfect. Thank you so much, Matt. And then last but certainly not least, we have Anuswa Trivedi from Microsoft's AI for Good Research Lab. She is the lead scientist there, developing advanced machine learning models and AI solutions for Microsoft's partners. As Kate mentioned, Anuswa worked with them at the Carter Center on their work reclassifying events for the Syria conflict mapping project, but has also worked on other projects with them and other organizations as well. So Anuswa, please go ahead. Thank you.
Thank you so much. I'm trying to share my screen. Okay, so hi everyone. I am Anuswa. I work for the AI for Good Research Lab in Microsoft. A little bit about our lab. It's about democratizing AI for the societal applications of the problems, and there are several different verticals that we have been focusing on. For example, AI for accessibility. If you're kind of looking at my screen, you'll see there is a live transcript of the PowerPoint that I'm talking about. It's kind of taking doing a live transcript of it. So basically making all products, Microsoft products, more accessible is one of our kind of core focus area. AI for Earth or sustainability, where we are kind of trying to work on the climate changes, global warming, negating the carbon impact that tech companies have. AI for humanitarian actions is some of the projects where, like the peace efforts projects come in, and we kind of collaborated with Kate and Katon here. And then AI for misinformation is a new vertical that we are working on, and my talk is around that today. And AI for health definitely is another vertical that we work on. So as part of our humanitarian action, we started collaboration in one of the projects which Kate presented today. But we learned a lot in the process. This was coming from a very tech background, being a research scientist and a ML specialist, and very low technical, domain expertise in the peace space. So learned a lot collaborating with the Carter Center, and kind of took the collaboration forward and started working with their democracy program. So Carter Center Democracy Program kind of leads election observations since 1989 across 40 different countries. And in 2019, they launched the Digital Threats to Democracy Initiative, and the project that we are working on is basically a part of it. So what is the threat of misinformation, and how is kind of correlated with the peace theme that we're talking about today? Misinformation undermines any kind of democratic institutions. So false narratives can foment unrest and incite violence. So that is basically where we come in, kind of trying to figure out what kind of misinformation spread can lead to political or any kind of other unrest and incite violence, and how we can stop the virality of the spread of this misinformation before even it can achieve to that violence level. So the mitigation efforts is basically monitoring the misinformation and disinformation to help the local organizations, surfacing the misinformation narratives to produce the most effective counter narratives, and targeted research for coordinated inauthentic behavior. So with this particular project, we have been focusing on in the US election and how things could have been done differently. What are the things that we learned from the US 2020 elections, and how we can actually apply or make this model generally applicable, more generalizable, and kind of take this forward to elections happening elsewhere, for example, in Kenya, right? So can we kind of take the learnings from here, define some kind of qualitative metrics, and take it forward to work on mitigating the efforts in other countries. So with that in mind, most of the misinformation that we have seen and kind of incitation of violence actually spreads in social media networks. So collecting data from Facebook and Twitter, we started collecting from 883 public Facebook groups and Twitter, along with Carter Center Democracy Program. And then we collaborated with NewsGuard. These are independent fact-checking companies and kind of have years of experience in the domain. And they kind of helped us categorize the repeat offenders domains. So for example, the domains which are very, very known to spread misinformation, either for willingly or in a malicious, with a malicious intent, either for a financial benefit or any other kind of benefit in mind. So media sources, so first of all, identifying that is basically the label that we are getting from NewsGuard or other fact-checking companies that we're working with. So repeat offender media sources are identified, and then we kind of train our model on that. One of the major problems of misinformation is the topic is ever changing. So it's really, really hard. And the language is also ever changing. I mean, you saw in Kate's project how IED was declining because just the language was changing a little bit. Imagine misinformation. I mean, before when COVID hit, nobody was even talking about vaccine hesitancy or, masking related, any kind of politicization of that. So nobody even thought about those kind of topics arising, or that could reach so much virality and could lead to so much conflict, or could become a threat to the democracy. So essentially kind of identifying topic preemptively and kind of stopping them before even they achieve virality is basically one of the main goals for this project. So we try to build a simple web-based tool for detecting and analyzing disinformation. The target audiences are hopefully the political entities, the human rights organizations, journalists, and the fact-checking companies. If we kind of create this kind of flagging systems for fact-checking companies, they can actually go and kind of see which of the news or topics are kind of achieving the virality, and they can actually that actually reduces the scope a lot. It just is at that point of time only kind of 5% of the whole volume of data that they're, because in social media, we generate such a volume of data globally across the world. It's really hard for humans who are domain experts to kind of go and kind of verify the authenticity of the news, right? But if we can actually create some kind of flagging system where the AI kind of acts as an assistant for the fact-checking companies, it kind of reduces their workload a lot and kind of helps them in the process. So there are different kind of approaches that you can take for like different types of data. Let's take the example for Twitter, right? So you have a UI, you kind of searching for a hashtag, it goes to your Twitter API, kind of extracts all the tweets that have been posted in the last 5 seconds related to that hashtag. And then basically you upload the data to your blob storage, that particular instance, the last 5 seconds data, and you run your machine learning model. Again, the machine learning model we are using is basically a large transformer-based text classifier, and it kind of is trying to say if the news is coming from a repeat offender source or not, and if there is, then what are the topics which are trending and how many times this has been retweeted. For example, for Twitter, the way they define virality is basically if a tweet has been retweeted for 10 times in last 3 seconds. So if there is more than, so when you're extracting the data, you get the tweet ID, you get the retweet ID. And so if you can count the retweet ID for a particular tweet, you can see whether if the number of retweets which are happening are more than 10 in the last 3 seconds. At that point of time, you kind of flag it. And even in spite of whether it's a repeat offender or not, it's something to kind of look across because it's kind of achieving virality. Because most of the time, if there is a news trending, a lot of correct information as well as misinformation is kind of trending in social network. And then comes the classification network, which kind of focuses on that, on those flagged viral retweets, and kind of tries to classify which of these are basically misinformation, which of these are not, and kind of flagging the misinformation so that the human experts can actually go and kind of drill down on them. Facebook data is a little bit more different. Facebook data is not only about, there are majority of like different components there where you actually can share a lot of, so Twitter snippet is much more smaller. Facebook can actually have a bigger post. You can share a link, you can share a video, you can share a joke with an image and the text embedded within it. You can share a GIF. It's not only a text related problem at that kind of time. And also one authentic news source link could be shared with a different sentiment or opinion, right? So just posting on the message, right? Which is true for both Twitter as well as Facebook, but the way Facebook and Twitter disseminates the data, the way you kind of get the data out, I have 2 different layers of views. So Facebook preserves its data access a lot more. So we had to kind of like work a lot more to extract more information out from Facebook, which we were kind of readily getting from Twitter. So getting those kind of Facebook data, we kind of do a sentiment and opinion analysis on the articles or the links which are being shared, as well as the Facebook message. You kind of do the emotion analysis where you're kind of trying to see the sentiment, and Facebook has more sentiments around a post. It has got 7 or 8 sentiments. I think in Twitter it's just 3. So you have a more variety of emotional analysis which you can do on the message and kind of gauge the virality. Whereas in Twitter they have a defined sense how virality is kind of tracked. Facebook do not have that. So you kind of need to get that emotional and the sentiment and the opinion metric to kind of then create an ensemble of it and come up with a virality score for that. As I was saying, the topics are ever changing. So for example, self-supervised deep clustering is another way. So basically where it's not completely unsupervised, but it's an unsupervised approach where you kind of give a sample of only a very small sample of a couple of hundred label data, and then kind of let the model self-train on itself so that it can kind of start extracting topics which kind of can achieve virality. So for example, if I've given it enough viral information before COVID, and then I start giving it COVID data, it would automatically start to learn that COVID is basically a viral topic, and anything associated with COVID will kind of be like pulled out. Then kind of topic modeling, and one of the collaborators we have are Global Disinformation Index. There is like long form text classification, short term text classification. We took it another level further. We kind of use the GPT-3, which is a state-of-the-art text classification system. It does not need a lot of data. It's amazing how far from like on transformer-based model we have come from BERT to GPT-3. Even if you can give it like 10 or 15 text examples, it can learn a very, very well supervised model at this point of time with GPT-3. It's amazing how big this kind of embeddings for this large neural networks are, and how less of an effort. Everything is like GUI based. You don't even need to be a ML scientist at this point of time to train a GPT-3 classification. You have access to one. So essentially what we are trying to get are basically features: sentiment, opinion, emotion, the article scores, the text classification article scores, the topics, and basically the cluster embeddings, and kind of create an ensemble of features where you can, at that point of time, helps define your qualitative metrics for tracking misinformation, because this is a very, very unsolved problem. Nobody even knows what metrics to even track to figure out which is misinformation versus not. So defining this kind of thing, this kind of metrics is what we have been working on, and we're working on with like the policy teams of Twitter and Facebook to kind of guide, along with UN, to guide them, on what are the metrics people should be looking at. I already spoke a little bit about the model on the short and long form, and how we have used BERT and how we have used GPT-3. Just on the visualization aspect of it, right? For example, this is one of the Twitter visualizations that we did. As you can see, there are like models that you can choose, so fake versus real, and you can choose the size of your network that you want to, this whole radius, right, that you want to work on. What is the exact hashtag? I just said COVID-19, and the last three, like, in the last 5 seconds, this many, when the query was given, these many kind of tweets were happening. As you can see, it's a lot in the last 5 seconds globally. But as you can see, this red person is basically that particular Twitter ID is kind of constantly spreading misinformation. That's not as harmful as this person who has a lot more followers, right? So this person do not have as many followers. There's not a lot of red propagations there. However, in here, as you can see, there's a green as well as red propagations, and so it's a big influencer. Bigger the influencer, bigger the red dot. And how much, how many more people they're influencing, the number of retweets, if it's, as I was saying, it's more than 10, kind of achieves a virality. So those kind of, the size as well as the number of retweets is something that we kind of like try to track. For example, here there's a big influencer who is kind of influencing both, positive as well as negative, sentiments or misinformation around it. Also on the visualizing the topics, right? What are the most trending topics if you think about, like, people are talking about along with like COVID-19. So for example, you're talking about coronavirus, you're talking about pandemic, you're talking about COVID vaccine. So along with COVID vaccine, what are the other things which are coming out? And I'm sorry, I had to concise this down for the presentation, so you might not be able to see the full thing, but kind of giving an insight, like how one hashtag related conversation can actually spin out and go to further topics, which could then in on its own end start achieving virality on its own side. So so we are still working on this project, and hopefully we'll be able to kind of solve this. Yeah, that is basically my talk is on today, and I'm happy to take any questions if any.
Great, thank you. So we have a few more minutes here at the end for Q&A. If anyone has any questions they want to drop into the chat, and give them a few minutes to do that. I can sort of start things off while we wait for questions to trickle in. I guess maybe Kate, I'll ask you a question. In terms of sort of applying this type of project to other things, is there like perhaps lessons learned in terms of what not to apply these types of models to? What projects or what types of data would not maybe be the most useful to try to apply NLP to, and maybe more traditional methods would be more useful?
That's a good question. I think in terms of reclassifying basic categories, for example, we have like a VLOOKUP as part of our ETL process or our transformation process for our data, that it wouldn't make sense to expend all this time and energy for an NLP to recontextual data if we know this equals that, right? I think sometimes there's a thinking that you should apply, machine learning and automation to something that sounds really cool. It's not worth the time and the energy. It should be something of value. And also, a text classifier, showing what Anusha was looking at, for example, it's a different type of automation. Text classification is good when it's really consistent language and consistent data. And even with that, with conflict data, you can see it is changing. But you just have to be really clear and be willing to invest the time to then lay out to that machine and that model, like what does this mean? What does shelling equal to? What does barrel bombardment equal to? Because it's on text. It's not going to work on just like randomly pulling data from the internet and hoping it turns out great, depending on the model you have. I know Anicia has a pretty amazing new model.
And I would imagine too, kind of like you mentioned, how the more complex, the more the language changes and the more sort of variety there is in the text, the harder it is to use a technique like this. So like really stuff that is consistent over time, perhaps, like that would lend itself better to these approaches.
Certainly, and if you're trying to have it derive more from the meaning, it has to have some type of language associated with it, if that makes sense. So if you're saying that you want it to determine that this is an assassination, let's say, but there's no unique language in the description that this is an assassination, you just know by the certain terms, the context that they use, that it might be an assassination, that might be something else you need to think about how to approach that. So yeah.
Awesome, makes sense. We're still waiting on people to ask any questions. Definitely feel free in the last couple of minutes here. If you have any burning thoughts or questions you want to send in. Rachel, I will ask you one. I'm wondering to what extent, we see a lot of data sets coming out these days that sort of are event-based, or perhaps they're sort of scraping news articles and websites to code events and sort of are machine-generated events. To what extent is ACLED, I guess, looking at things like that to sort of use machine learning to sort of phase out any of the human research work?
Good question. So I think, we're out of time. I can very quickly answer. I think you can't use these sort of models to completely supplant human intelligence and human instinct. I think we're always going to have a need for human researchers in this process, and we really need to see machine learning as a tool to decrease maybe the amount of human hours that you need to put into something, but you always need to have that human element and a human eye cast on the data to make sure that things are accurate, especially with something as as sensitive as conflict data. So that's my short answer, since we're running out of time.
I definitely agree. Yeah, I think the one main takeaway from all of the presentations today is that this is definitely a tool that can be used to increase efficiency and to cut down on manual work hours, but that as we see, it's not perfect across the board. So thank you, everyone.